Hi, this is the video for today for April 22nd. I want to just quickly touch on the things that are due this week. It's our last week of class. The assignment number 9 has a hard deadline tonight. And if you made an 89.5 or less on exam 2, the exam 2 autopsy is due Thursday. I will be having Zoom office hours tomorrow morning from 7:30 until 9 and by appointment on Calendly. You can find the link to making a personal appointment on my syllabus. And I also will plan to have in-person office hours at 11 a.m. on Thursday. If you want to get any last minute help, I wouldn't start it then. That's not a good idea. If you have to do the autopsy, you want to come there with it completed and just confirm that what you are doing is correct. The assignment 10, the task 4, class project regression analysis, is due on Monday. And I have posted the instructions for that on Brightspace now, so you'll want to go over that. We're going to go over it more on Thursday. Okay, if you want to get a head start, that's probably a great idea. We're going to review the multiple linear regression. All right, that's what MLR stands for, with the rental data. So the rental data is the second worksheet in the workbook file we downloaded out of Brightspace. So if you go to Brightspace, you can, if you have it from last class, last Thursday, you can get it. If not, go to the data module in content. And in the data module, come down to at the bottom, regression example data part 2. Right, so go ahead and open that. Let me see if I have it open. I don't. Okay, so get that open. And we're going to start with the rental data. So this right now is the steps that we are on for performing multiple linear regression. And I want to make sure that you have good modeling practices. So many people skip the first few, and I'm going to, in some sense, skip some of them, but I don't want you to think that that's the way you're supposed to do it. So here's the data. Okay, I'm going to go through this. Some of this stuff we've done before, so I'm not going to go super slow. You have the luxury of having a video, so you can stop and rewind if you need to. Okay, so here is some rental per month for some apartments, and how many bedrooms and how many bathrooms and what's the square footage. Okay, and we are asked to develop a regression equation, a model that will help predict the rent wherever this town is, wherever this place is. I don't have that information given this data. Okay, so obviously it doesn't apply to like New York City, Manhattan. Add another couple zeros there, maybe. I don't know, maybe not that bad. All right, but anyway, so let's go back to our list here of the steps. We're going to check that the data is clean of outliers, or decide if we're keeping or deleting any of the outliers. So let's quickly look at that. Okay. So I'm going to start with the rent. We all know the trick of looking for the box plot. Okay, no outliers in rent. So I'm just going to delete it. Okay, now I'm going to look at bath. Yeah, I do see an outlier for the baths. So number of baths. Sorry, I take it back. I think this was bedrooms. Yeah, number of bedrooms. Okay, I'm going to move that up to the top, like right here, and make it nice and narrow. I don't want to take up a lot of space. I'm going to be working horizontally. You could potentially add more worksheets or work horizontally. Kind of depends on what you find is least annoying. All right, so now I'm going to look at bath and see if there is we also have an outlier here. So number of bathrooms. Okay. So we're seeing that we do have a couple outliers in this data, and then square footage. And we have 3 outliers in the square footage. All right. So now that we have that, we have to decide what we're going to do with these outliers. You don't always have to delete outliers. Sometimes outliers are real, like the real variability in the data, and they become important in a sense. Remember, they're always influential. The question is, are they influencing away from a trend? So let's go ahead and get started. So there's the first 3 steps here. Check the data if it's clean of outliers, or decide if you're keeping or deleting, run correlations, and confirm linear relationship and find candidate predictors. So those first 3 steps are sort of all done, if you will, in a at once or all together, or you could think of it as going around in a circle. Okay, so we're going to decide what we're going to do after we get a little more information. So we're going to be working on 1, 2, and 3 right now. And then we'll decide what we think we should do. Okay, so the first thing I'm going to do is run the correlations on my data. And this is part of that initial exploratory data analysis that we're doing. We kind of want to understand what are our candidate predictors. All of these, remember, we set the threshold pretty low, absolute value of 0.15 or more. So these all look like they're candidate predictors right now. And we look also for 0.7 or higher correlation. So here I'm seeing a couple right here. Turns out if bathroom, so let's, I mean, we have to confirm this with a scatter plot, but right now we're seeing numbers. So this 0.67, I'm going to actually include it. And the reason is, if you think about it, the number of bedrooms and square footage makes sense that those would be correlated, because the more bedrooms you have, right, the more space you have, unless you break up a big room into little bedrooms. So there's exceptions, but usually there is a correlation, and we see this 0.82 number. And we see that square footage is correlated with bathrooms. So the more bathrooms you have, the more square footage you have. So that kind of makes sense. And the number of bedrooms and bathrooms are also almost on the threshold of being correlated, but I think it's close enough that we want to think about all 3. Okay, and we may, this one, maybe if you want to make it not quite as orange, if you want to say like, okay, there's like a kind of a question mark here, we can do that. It's kind of notes to yourself, really, things you don't want to miss. All right, so now we're going to confirm these regression numbers are linear. So I'm going to have to put the data on the right. So let me copy that. So I can have the rent, which is my response variable, right? We're trying to predict response, and we're going to use these predictors. These are our candidate predictors. And so let's just go ahead and make sure that we actually have linear relationships, which is one of the first assumptions, right, that we talked about on Thursday. And it's always going to just give you the y-axis. So, right, so we have rent versus bedrooms. All right. And I'm going to do some things in this lecture just to save time that I hope you'll forgive me. It's not the way I would do it if I was doing regular work, but I just want to save a little time. I'm not going to worry about all my axes if I have my chart label correct. Okay, so that's that one. Now we're going to do number of bathrooms and rent. I don't know what happened just now. Okay. So that looks linear. These two both look linear. Let's try the last one. Okay, so now what we want to decide is the multicollinearity. Excuse me. So let's go in and check that. That's going to help decide. Now, obviously, as I go through this, um, I don't see this in the number of bedrooms, which is the outliers out here at a 5. That's that point right there. I kind of see it kind of trending where the trend line is. I don't see it influencing the trend line away from what would norm be a trend line if it wasn't there. So I kind of feel like that one's not a problem. Now, when I come to the rent versus the number of bathrooms, I have 4. So this dot right here represents 2 points. In other software, better graphing software, you can get a wiggle and you can see that it's 2 points probably right there. So we have 2 there because I see them right here. All right. So I also see that if you remove them, they might be a little influential, but if you kind of erase those from your mind's eye and look at where you'd put the trend, it may go up just a little bit more, but those actually look like they're anchoring in the right direction. And what looks like more of a problem are these up here. Anyway, so jury's out on that one. And then when we look at this one, we definitely see a problem with this influential observation because it's definitely pulling that trend line down towards it. Okay, so that might be the one that we are concerned about. All right, so now let's check for multicollinearity. That's going to be our next thing. And I guess it's really the first 4 steps, right? What am I talking about? Just to remind you, the first 4 steps. So the first 4 steps, we kind of do them in a round robin kind of way. We're going to go around and make sure we've identified basically where our full model is going to start and what data we're going to use. Do we remove the outliers like you need to check with the sensitivity analysis in the homework that's due tonight? So if you need help with that, I made a video on how to do that and what to check for, but I'm going to also do it here. Okay, so now I'm going to check for multicollinearity. So I need to check, let's start with the worst one, square footage and bedrooms. So when it comes to multicollinearity, they're both predictors. It doesn't matter which one is on the y-axis or which one's on the x-axis. We are just trying to determine if they are landing on a line. Okay. Okay, we add a trend line here. And we have square footage versus bedrooms. All right. So it does appear there is a linear trend, and that influential observation value way over here we see is actually way out of from the rest of them. So again, confirming even more that this may be um, an observation we don't want to include in our regression analysis. Remember, regression analysis is very sensitive to the influence of outlier data like that. It will change everything because it's, if you can think of like a seesaw, it's like, you know, you're just pulling the straight board towards that point. Okay. The next one we're going to check is square footage and bath. So square footage and bath. And I'm not, right now, I'm just don't want my video to take forever for you guys. So I'm not putting in all the axis names and all that stuff. But when you do assignment 10, you do want to have, you do want a good final assignment. Okay. The last thing to check is this one that we did in the like peach color, bed and bath. Are they linearly related? And sometimes those correlation numbers, when you have discrete numbers like 1, 2, 3, we're counting, the correlation is not, doesn't show up as strong, yet it could be there. So that's why we always also want to check with a graph, a chart. All right. So we do see a lot of spread around this line. And obviously, if you have 3 bedrooms, it looks like you could have from 1 to 4 with 3 bedrooms, you could have from 1 to 4 bathrooms. So yeah, that's weird. There's actually an apartment in the state that has 4 bathrooms for 3 bedrooms. Full. That's full because the half is the 0.5, right? Okay, so that's weird. But anyway, so we do see it appears like they are linearly trending, although there is a lot of variability at the 3 bedrooms. But okay, so let's create our little table that is what you want to have as your output. I will be looking for this because this is really your marching orders on what to do next. So we're going to have the full model. And if you need more space, put this somewhere else. But for us, for today, for this example, we only need a little tiny bit of space. Okay. So we have the full model. Let's make these a little bit bigger. All right. And the full model. So we have to pick one. So I think this implies bathrooms and bedrooms are close enough that we don't want to include, and at least initially, we're not going to include them all. And we may come back and test it later. We'll see. So I would say we have to pick between square foot, bedroom, and bathroom to be our initial predictor. I am going to give you a little modeling tip. It's not a hard and fast rule, but if you have more continuous data like the square footage versus the discrete numbers like counting beds and baths, we're incrementing by halves on the baths and by whole numbers on bedrooms. Usually it's a good idea to go more with the continuous one. It also has a stronger, oh no, it doesn't. Bedrooms is the strongest, but I think that that could change once we take out this influential observation. We'll see. Anyway, so I'm going to suggest we start with our square footage. Again, this is a judgment call. You're going to start with one and we're going to swap out um, bath and bedroom, number of bedrooms and number of bath. Okay, so let's make this our little table. Okay. So now what we need to do is consider this, that influential observation to decide what we're going to do. All right, so consider, first of all, the model with all the data. Okay, so that's just our first initial square foot is our predictor and rent is our response. So it's a simple linear regression. Make sure to have labels checked. I'm moving horizontally, so I don't need this last bit of information. I'm just going to clear it to give myself more room because it's just a repeat of what's here. The reason it's there is because by default, Excel will always give you the 95% confidence interval around this coefficient. But you have the option to do 90%, 80% other ones, and that's what that output is trying to state. Okay, first thing we're always going to do is check for a green light here. Okay, now let's look at those p-values. If you don't like them like this, change them to numbers. But you definitely want 4 or 5 decimals for the precision. All right, so this is looking like another green light here. Okay. All right, so this is where we're at. And so let's say we're, I don't know, I put that in yellow, I guess, model with all the data. All right, so now we're going to look at the model removing the influential observation. All right, so we need to go in and find that, right? So maybe I should actually also tell you, let's give this a little more serious of a title. We'll call this the sensitivity analysis, where we're trying to decide if we're going to remove the outlier or not. Okay, so let's put a little title on that. There we go. Okay, so I'm going to get the data over here. So let's get all this data because we want to, if we're going to delete anything, we're going to delete it from all variables, right? We're not just deleting square footage. We're going to delete. Remember when I showed you how to clean data, you clean, if you remove an outlier, remove the whole, delete the whole row. I didn't like that. Let me try that again. Okay, so on here, let's get those filters added and go find that super large square footage one. Okay. All right, so what I'm gonna do, now notice I have I can't delete this whole row like we did because I'm kind of working on one worksheet, so I have to be careful. This is just a little Excel stuff, but I don't want to delete the whole row. I'm just going to actually make a copy of this. So remember, we're gonna keep track of what we delete. So I'll put that right here. And and it'll show up after I take the filters off. But for now, I'm going to also now select the actual numbers and clear the contents. All right, this is not the way we did it before, and you could do it the way we did it before if you want. I'm doing it this way because I want to work on one worksheet. Okay, so I'm going to delete where I made those blank. I'm going to shift the cells up because I need to have no blanks in there, and this got left way down here, so let me move it. Okay, so let me say I'm going to delete this observation. And let's put a yellow highlight on the reason why. So again, a little bit of a review of everything we did back in, well, one of the steps we did back in the first third of our course when we were learning about data prepping. Okay, so we're going to delete that observation, and now we're going to run the regression again. So I'm putting in my rent that has that one observation removed, and now I'm putting in my data for the square footage. I'm going to still run the same model over here. That's the full model. So I'm going to go with square footage because I want to be able to compare apples to apples. So I'll go ahead and put that here. Okay. All right. Whoops. Again, I don't need a repeat of the same exact information. So annoying. That's new. That didn't used to be there in Excel, and I wish they had not done it. I wish they could override. Whatever you pick just goes in one spot. I don't know. Okay, we're still in the green for go on the joint significance. Remember, this is your joint significance p-value is what is in green, right? We need that to be green. That's our first green light. A lot of little steps here that in other software, you could set it as the default and it would always be giving you this, output. You just always get the same kind of output. Okay, so now that we've done this, what we need to do is compare the output from the model with all the data and the model with the influential observation removed. So let's just go ahead and set up a little table. Let's say this, we're going to look at all data, and really what we're going to compare, the p-values in both are significant, and they're 0 to 5 decimals, 6 decimals. Wait, I can't count. 1, 2, 3. Yeah, 6 decimals. So what we really care about are going to be these goodness of fit measures. Whoops. The adjusted R square, the R square. Notice that in both of these, we have the same number of predictors, so we can actually compare R squared if we wanted. All right, so let's go ahead and get all data, and I'm going to grab R squared, adjusted R squared, and the standard error. Put those right here. And then for the sensitivity analysis, I'm going to grab the same thing. I'm only going to get the numbers this time, though. Okay, so we have a nice little table. Oops. And for these numbers in here, you can usually just compare them with 2 decimals. If you need to go out, you can add another decimal if they're tied. All right, so head-to-head competition, sensitivity analysis has got an adjusted R squared of 0.85. Notice these match, and that's because we only have one predictor. So when you start with a simple linear regression, the R squared and the adjusted R squared are the same. Anyway, head-to-head, this wins for sure. 0.85 is definitely better than 0.7, and we see that we also have a lower standard error as well. Okay, so We're going to have a decision here. So decision is to proceed, right? Is we're going to proceed with data that has influential observation deleted. All right, so we're going to use this data here going forward for the rest of our model building work. Okay, so now that we've done this much, okay, now we have to swap out for the multicollinearity question, because that's the next thing that we want to do. All right, so let's begin by beginning our comparison. So let's see, I'll go here and I'll say check swap. I think I was just giving them swap out models. Checks for multicollinear. We want to find the best of these three. We want to find out the best of these three possible predictors. So we're going to do checks for multicollinear predictors. All right, so the first model is going to be our square foot model. All right, so that's the one we just got done doing. All right, so we have the square foot model, and we're going to have the predictors. We're going to have the coefficient, and we're going to have a p-value on those coefficients. All right, so let's go grab that. So that's going to be here. And we're going to get those p-values. The intercept p-value is not, we don't really care about that one so much, right? All right, and then besides this, we're going to also want the same data that we got a second ago on the goodness of fit measures. Put those here. Okay. Oops, I messed up. Okay. So now we're going to add in, we're going to swap out. All right, so we got to do a little swapping out here. So let's see, I'm going to come here and I'm going to do that below here. All right, so I'm just going to go, I'm not going to go totally horizontal. I'm kind of going vertical on the multicollinear, I guess you could say. Okay, so now we're going to swap out. Square feet with bedroom. Or let's start with bath, since that one was a little more highly multicollinear. All right, so notice I am giving lots of good information as I go on what I'm doing. Okay, so you don't want to have just a big mess that's impossible for anyone to follow. So don't do that to me, and don't do it to colleagues as a general rule. In the real world, someone always has to check your work, because we are not perfect. We all tend to sometimes make mistakes, right? So you're going to always have a process of quality control um, in the work world. Okay, so I think I didn't need to do that one, but I do need to switch this now to bathrooms. So let me get the number of bathrooms here. Put that in. Excuse me. Labels, output range, though, I got to change. So I'm going to put that output range right here. All right. Okay, once again, I don't care about this part, so I'm just going to delete it. And the other thing, you can't just right click and delete. There's no like delete. Well, I guess there's this. Maybe I could just right click and delete that. But it doesn't get rid of, well, let me see. Shift cells left. Okay, what happens? Okay, that works too. Never mind. All right, significance. We still have a green light with this one, so we're good to go. So it's a contender. So finally, if you still need to keep doing this, that's fine with me. But, I might skip it just to save a little bit of time. Okay, so now we have this one. So now let's put in our results into our modeling table, our comparison table, our results table. So that is going to go here, I believe, and we're just going to copy this part right here and rename this the bath model. All right, let's go grab those p-values. And let's grab the goodness of fit measures. Okay. All right, so we're going to have a three-way battle here because now we're going to swap out the third multicollinear predictor, right? So we had square footage now, and we ran it with bathrooms, and now we're going to run it with bedrooms and see what happens. Right. We have a green light on this model as well. And we have green light on the p-value is also significant. So they're all good candidates from that point of view. Let's put this in here. So I'm just pulling out the part of the output that is going to be driving my decision making. So I'm pulling out the goodness of fit measures now. All right. Okay. And what I told you about these is that they can be in 2 decimals usually is sufficient. Well, see here we can't. So both of these, we need more decimals. Oops, sorry, wrong button. All right. All right, so in a head-to-head, um, we're seeing that it looks like we have a tough competition going on here. And somehow, oh, I got the wrong information. I was like, wait a second. Yeah, 147.9 for the square foot model. Yeah, so I accidentally grabbed the all data. For goodness of fit, I was supposed to grab these over here. So let me grab these instead, right? Because that's this output without the influential, the one we're decided to proceed with. That's these numbers right here. I just copied them down here and already formatted them. So let me put those here. Sorry, that's what that should have been. Okay, in a head-to-head, it definitely wins. So square footage, I knew something was up because I remember doing this, preparing for this lecture, knowing square footage was a clear winner. Okay, so we're going to call this our top contender. It's not declared as our final model yet because we still have more work to do. So we'll go ahead and call this one, the square foot model, as our top contender. And I'm going to give it like a light green color or something. Okay, so that's where we're at right now. All right, so now what we want to do is very carefully, now that we know we have a good stable model that we feel makes sense, because we do expect, and let's look at this coefficient, 0.8695. So what that's saying is for each additional foot, it's square footage, right? Each foot additional that the apartment is bigger, the rent goes up by 87 cents. Okay, but that makes sense. We expect for bigger square footage, the rent to go up. All right, so now what we're going to do is we're just going to check if adding back in the multicollinear predictors helps the, the fit. All right, and part of the reason I want to do this is because we had that 0.67 of bedrooms and bathrooms weren't that highly collinear. So let's just see what might happen. Now, once we introduce multicollinear, so let me just remind you of this. When we introduce multicollinear, hold on. It turns out that, sorry, I'm going to the wrong slide. All right. We might have some imprecise issues going on. So really, since the only other model that we could check that would make sense for us to check is having bathroom and bedroom both in the model, because perhaps that model would be better than the square footage model. So let's just compare that. So we're going to check model with we know that square footage is highly correlated with both bedrooms and bath. So for those, we just want to switch them out because we can't trust we can't put them back in, but let's try bed and bath together because we assume those were correlated. But it's only a 67% correlation. So let's just see what happens there. So I'm going to rerun this analysis. It's still the same rent, but our predictors are now going to be the bed and bath data. Okay. And let's put that location as right here. Okay. We do have a joint significance with this model as well. And we want to look at the p-values. And we see that they are also significant. So this model is a contender. So let's add this model to our table. All right, so let's copy now these coefficients and predictors. So this is the bed and bath model. And we're going to get the goodness of fit measures for this one. All right, notice that our table's a little off. So if you're okay with that, that's fine. If you're not okay, maybe you want to add in a row, some data in here, insert, shift cells down, and that'll line up everything. Get a little weird formatting you can fix if you want. I'm not going to do that right now. All right. All right, so we have not dethroned the top contender. The top contender still wins because 0.74 is less than 0.85, and we want the biggest R squared possible. We see the standard error went up when actually we want it as low as possible. So the top contender still remains our top contender. Okay, so now that we've done that, what we're going to do is continue to start doing modeling checks. Right, so I think this is then almost to where I want us to catch up before we learn more about the assumptions. So we're going to do the model assumption check. So I'm going to create another table for model assumption checks. Okay, and some of these we've already inherently built them into our modeling because we checked that there was linearity. Oh, sorry. I meant to put this down one. So the assumption is linearity. And we want to know if it's violated and what is the remedy that we will do if it is violated. Okay, so okay, so linearity is going to be something that I told you. If you see a linear trend in your correlation, and we're looking at square footage down here, rent versus square footage, that point's now removed. So this is going to be a better fit. We are going to assume, or not, sorry, we're not going to assume, we are going to be hopeful that we don't have a linearity problem. But the residuals will be, the residual plots will be a better check on that. So I'm going to rerun our final model. And this time I'm going to actually get the outputs. So running that final model, again, but just getting slightly different output that now I'm going to start focusing on. So the rat is correct, but my predictor is going to go back to being just square footage. So let me come here. And this is the data with the without the influential observation, which is what we're going forward with. And my output range, I'm going to select my new output range. Start, I think I'm going to start it like down here, maybe a little lower. Okay, now here I'm going to click residuals, residual plots, standardized residuals, line fit plots, and normal probability plots. All right, so I checked all 5 of those boxes because we are going to want to go through that. Notice that the plots got put way over here, which is so annoying. So I'm going to just select them all by holding down my control key, or on a Mac, the command key, and cut them all. So control X or command X. And let's just work over here. Whoops, too far. I'm going to just put them right here for now, and we'll look at them as needed. Okay, so first of all, save space. Okay, so this is everything that we've already worked through. Nothing should change. You should make sure you have the same information, just as a sanity check. A 0.8696, a 147, that looks the same. And we have 0.85, 0.85, and a standard error of 155. Yep, so we have the same model. All right. And so the first thing we're going to do is look for linearity by looking at the residual plot. So here's our residual plot. Okay. And what we would like to see is that I showed you that gold standard of residual plots. So this is not quite there, but we have what we're hoping to see is a band of data. But what we don't see here is nonlinearity. Like, you don't see a pattern of like a parabola or an S shaped or a wiggle of some sort. So linearity does not seem to be violated, so that's good. So there's no remedy needed. So NA, sorry, I was trying to type NA, not applicable. All right, the second assumption that we're going to do is multicollinearity. So if this bed and bath model had been better, then we would have, if that had been the top contender, then our multicollinearity would have been, we would have said it was acceptable. We had some, we know there's a little bit, but we feel like it's acceptable. So we, in this case, though, we only have square footage in our model. So there's no multicollinearity. With one predictor, you can't have multicollinearity. So we're good there too. All right. The third thing is what we're going to be talking about next. So let's go switch gears now, because I haven't covered it yet, and get back over to where we are in the lecture notes. Okay. So we are down to 6. We've gotten this far. And my question is, when you review the multiple linear regression with rental data, what steps involve checking for individual significance for each predictor with a p-value threshold? And for us, it was 0.05. So you can pause the video and answer that question on Top Hat. Okay, now I'm going to talk about assumption 3, which is constant variability of error. You don't want to have heteroscedasticity, which is not a word I'm going to hold you to, but that's what it's technically called. A lot of times you see this in cross-sectional data, and that's what we have. So we wouldn't be surprised if we see some violation of this assumption. What does that violation look like? I'll show it to you in a minute. I actually already saw it in the data. So it exists when the variability in the response changes with at least one predictor variable. So what that means is you have residuals that are changing as you move as the predictor variable changes value. The good news is the estimates of the coefficients are okay, the R squared is okay, and the standard error is okay. What's not okay are the p-values, both for the f-test, which is the joint significance, and the t-test, which are the individual. So you can't, if you have this problem, you can't really trust your p-values in a step-down procedure. All right, so it can also be caused if you leave important predictors out of the model. All right, so the way we're going to detect it is we're going to plot the residuals against each predictor variable one at a time. You can also look to see if you see it in the predicted values, and Excel doesn't automatically give you that. So I'm going to skip it because I think this is a lot of work already. You should see the residuals randomly disperse. And if you see something that looks like a triangle or fan shape, cone behavior, that's when you are in, you know, you might have this. So let's go back and look at what we have. So if you look at this residual plot, you'll see that there appears to be, let's see if I can draw in here, sort of a fan shape. And that as the residuals get bigger, it seems like the spread gets bigger and then it flattens out over here. So kind of we have more below than above, but can kind of blur your eyes a little, but there does seem to be this growing change, right? All these points right here are all kind of close to the x-axis. And then they start getting bigger. So it appears like it fans out, right? So it does appear like we might have this problem. To fix it, if you have to do step down and you want to trust your p-values, there's something called the White's robust standard errors, which are not available in Excel. And they are available in other packages, namely R, which is considered the gold standard for data science type work. Although Python is quickly gaining ground as well. There are many other more advanced techniques on what you do to fix these problems. They're beyond the scope of our class, but they involve changing the form of the predictor or the response. Like one initial thing people would do is it would take the natural log of the response, and that a lot of times can help the problem. Okay. So if we include bedrooms, we see a residual plot like that, and the square footage, the one I was just showing you, looks like that. And like I said, the adjusted R squared, and standard error are still useful, even if you have this modeling assumption broken. So going back over to our Excel data, let's put in our third assumption that we've been checked just now, constant variability in residuals. And if you have a multiple linear regression analysis, so you have multiple predictors, you want to check this on each one of them. Okay, and so for us, we do have it. We are violating this. We have this problem, and it's going to require advanced techniques. So we're not really going to be dealing with this. We're noticing it. I want you to be able to notice it. I want you to identify that you know it's a problem. Okay. Sorry, I didn't mean to put a box around the whole thing because we have more ones. So the way you get rid of a bottom box, by the way, is you go all the way down here to more borders. You've selected where the borders are that you want to fix, and you have tells you each position. So I'm going to delete, it toggles them on and off. So I'm toggling off that. Okay. But what I do want to do is highlight that this is an issue. So let me put a little orange on that one. Okay, so we got that problem, but we've identified it. All right, so let's keep going. The next one is the error term is not correlated with time. So conditional and the predictor variables, the error term is uncorrelated across observations. So you have, we want to avoid this. We do not want serial correlation. So serial means you put the residuals in order. And by order, usually this is something that we want to make sure is not a problem if you have time series data. This is where you might see it. Again, the good news is the estimates of the coefficients are okay. But if you have to refine your model, pick which is the better model, what can happen is all the standard errors are inappropriate. They're distorted downward, making the model look better than it really is. And so again, the t-test, the significance test, the t-test, and the f-test on the joint significance are can appear significant when they're not. So how do you figure this out? You have to plot this residual sequentially over time, and they should show no pattern. Sometimes you see positive or negative, like a flipping up, down, of residuals, and that is a sign that you have this problem. In R in Python and other software, there's something called the NUI West robust standard errors, which recalculate the standard errors that go into the p-value calculation, and then you can trust the p-values on the individual predictors. And for us, this is beyond the scope of our class. But in the data, there is a third data set on a sushi restaurant, and it's the sales, how much was spent that month in advertising, the sales for the month in thousands of dollars advertising, and what is the unemployment rate in that month, in that town. And the idea is, do either of these, are they predictive of sales? Okay. So if we skip a bunch of stuff that we should be not skipping, but just for the sake of time, right? So if you skip, so let's see, let's just go in here and say, okay, skipping the following. 1, outlier detection. We should have done that. 2, correlations. 3, multicollinearity. Check. Okay, we're skipping all that. We're going to jump right to running oh, and the other thing we're going to skip is step down. Step down. All right. So skipping a bunch of stuff you would normally want to do, and just jumping to a multicollinear, multiple linear regression. Where we want to predict the sales. And we want to predict those using advertising and unemployment. Okay. I'm going to put the output. Like right here. And we're going to get all of this output here. So, okay, we'll go ahead and do this. All right. So, deleting this. We have our initial significance tests. All right. But let me remind you, we think we have it, right? But let me remind you, right? That may be if we have this time, so this is time series data. So immediately we have to be like, okay, wait, we need to make sure there's no serial correlation in the residuals, in which case we would maybe not trust the test statistic on the FSA test. So let's make sure, actually, let's remind ourselves, let's put this in here with a warning. We don't really know if we trust it. We don't know if we really trust these p-values either. And so we have to check. When we look at the residual plot, it looks good. When we look at the unemployment plot, it looks good, right? And this line fit stuff we can talk about later. It can hide sometimes issue. Okay, so what we want to look at now are the residuals, which are down here. So here are residuals. I went over what those residuals are. So we put in the for each row in our data. So advertising at $550 that month, an unemployment rate of 4.6. We plug that into this model and it's going to give us the predicted sales. And then if we take the predicted sales, which was 28.944, so $28,944.91, and we subtract 27,000 from it, we're going to get a residual. And that's one of the things that we want to look at over time. Now notice that the month in the data is ordered, right? So month 1 through month 17, and that is also corresponds to the observations here. If not, we would want to put the month in here and sort everything in chronological order. But we can now do, we can actually graph the observations and the residuals and, whoops, with a scatter plot. Okay. So you can see that we have what appears to be, so let's say residuals over time. So here we can see that we have what is not, does not appear to be sorry, let me state that more clearly. It does appear like we have some kind of issue going on here, right? So see if I can draw on here. It does appear that we are going up and then possibly down and then back up. So there is what is called a serial correlation. So we have a problem and that's what that would look like if you have that problem. Okay, sorry, not the last one. Assumption 5 is that the error term epsilon is not correlated with any of the predictors. This breaks down when you, if you've left out an important predictor variable from your model, although it can sometimes not break down. You could have it anyway. What happens is all your estimates are unreliable if that is the case. And how do you detect it? You have to look for a correlation between residuals and predictors. So going back over to our rental data again. Okay. Looking at we have one residual plot. Sorry, I'm moving. Let me see if I can just erase all that. Okay. So there does not seem to be any correlation here. Okay. So they're not all like trending up on a line or trending down or having like a parabola. There doesn't seem to be any linear correlation or nonlinear correlation. It's just a blob that seems to be getting wider if you look at it from top to bottom as you go from left to right. Okay, that's that fan shape. We already talked about that. Okay, so let's go ahead and put in this fourth was no serial correlation in residuals. And this was not applicable, right? Because we don't have time series data, so there's nothing to do here. And the fifth one was that there was, let me make sure the way I worded it, the error term is not correlated. So let's just say uncorrelated error term with predictors. let me go ahead and put in residuals here. And this is not violated, so there's nothing we need to do here. Okay. Okay, let's keep going. All right, the last assumption is that the error term is normally distributed. So if this is violated, we have estimates of the coefficients are still okay, right? But we need this in order to construct intervals around the estimates in the hypothesis test. Again, same thing as before. We have a problem trusting the p-values. So what does this mean that the error term is normally distributed? So here's the residuals. Here is a predictor, and I told you this was sort of the gold standard. You want a band around the x-axis with the same general number of points above and below. What we really want is that if you were to project all that data onto the y-axis and make a histogram out of it, you would have a normal distribution on the y-axis. So we're going to look for this. One thing is when you look at residuals versus predictor and you have more points either above or below the horizontal axis, that means that the mean of the normal distribution is not zero. So that's a problem. You can check with histograms, even though they're not they're not considered a really great indicator as much as a normality plot is. You may have remembered learning normality plots in your 210 class. Sometimes they're called QQ plots. If you have this problem, you have to possibly do a nonlinear regression, which is more of the stuff in chapter 8 that we're not going to have time for. And there's also some more advanced approaches. Okay, so what I'm going to show you is how to check the normality plot if you're not sure if you have this problem or not. So when we run the regression, we're going to check normal probability plot and standardized residuals. And we're going to copy those standardized residuals, sort from low to high on them, and then plot them versus the percentile that Excel generated for us for the data versus the sorted standard residuals. And we want that data to be on a straight line. So let's go see how to do this. All right. So there is a confusion out there that you have to make sure your response variable is normally distributed. That is not true. So it's kind of really bad that Excel does this, because this is not what you care for. This normal probability plot should not be here. So that's not really appropriate for Excel to make that. But the fact that it makes it, I wish it made the one we actually need, which is the standardized residuals with the sample percentile on the x-axis. So let's go ahead and take those standardized residuals. This is how we're going to do it. And copy them to the right over here. And then we're going to sort them. So let's just say sorted. Okay. And we're going to select just this column of data. And we're going to sort it. So we're going to go to data and sort. It wants to tell us, hey, you need to expand, because if not, you're just going to sort this column. We're going to say, nope, that's exactly what we want. We want to continue with the current selection. And we're going to go from smallest to largest. And then we're going to graph the percentiles versus the sorted standard residuals. And this is going to tell us if our data is normally distributed. So what I would recommend is that you go ahead and add in here, where is it? Insert in the shapes, find that straight line and just try to draw a straight line on here. Don't do the trend line because it's not really going to work for you so well. But so we have a section of our data that appears to be okay. And when we have an area over here that does not seem to be so okay. So we can go up here 6 and say that error is normally, this is the assumption, distributed. And we're going to say, is this violated? Is this violated? Well, it sort of is. So it is not a terrible, terrible model, okay? Because we have, like we said already, we have like an 85% R square on it. And the R square we can still trust. All right, but we can't build any confidence intervals around the predictions. There's a lot of stuff we can't do. So we really probably would want to do some nonlinear regression and see about if that model is better. So we would say, is it violated? Partially. So remedy is going to be advanced techniques that are beyond the scope of our class. So again, let's highlight this one as possibly a little bit of a problem. So anyone who looks at your model, or if you communicate this model to someone, you have identified the shortcomings. All right, so you would need, if you find this and you've already, everyone assumed it would be standard, linear, and it's not, then you might have to renegotiate your contract because it's going to take more time to do a nonlinear regression. Okay, so I'm going to come here to this in a minute. Square foot line, okay. Okay, so according to the information, which method suggested to detect is suggested to detect if the error term in a model is not normally distributed? So you can pause the video and answer this question on top hat. Okay. So final check. And it's not, maybe check is too strong of a word. Final kind of results, and these are called line fit plots. It shows the values of the observed response. So in this case, it's the blue triangles for rent and the predicted response for each value of the predictor in the sample data. Okay, so we have these predicted response. You can see it's a little off in a couple places. This is the equivalent of a trend line. If you have only one predictor, but if you have multiple predictors, it's going to give you for each predictor. So I ran a model with bed and square footage to kind of show you this as an example. So you can see as, even though it's not the top contender, it's not the final model. I just wanted you to see that this is, if you had run a model with 2 predictors, you would have had, you can't do a trend line because we're talking 3-dimensional. So this is the equivalent of what you get for a trend line. So as the value of bed varies in the data, what is the predicted rents? And it will pull in whatever the square footage was on that row to help figure this out, but it's just showing you how it did. And then square footage, as that varies, it's going to show you what the predicted rent is using the bedroom numbers that were on that row of data to calculate the predicted, right? And so you can see it kind of follows the line, right? We see the linear trend. But we see that there were exceptions that the model was not able to predict. So perfect is usually impossible, but you hope to be close. Okay, so a model building strategy. Identify the numerical response variable. Identify all reasonable predictors. Make sure you use ones that make economic and intuitive sense. You want to clean the data, or at least identify the outliers. Definitely, if you have dirty data, you want to remove the missing data, you want to look for typos, all that stuff we did. Run correlations and scatter plots for numerical variables and contingency tables for categorical variables to determine which numerical predictors are linearly related to the response variable, which dummy variables appear predictive of the response, identify if you have multicollinearity among the predictors, and choose which predictors to start with for model building. Then you're going to start with the full model and check the joint significance if it's less than 0.05. And if the coefficients, look at the coefficients, and you're going to drop the one with the largest p-value. And then you're going to run a reduced model and compare the goodness of fit and the p-values of the coefficients, and continue reducing the model until you have a preferred model. And notice we haven't been checking if we can even trust those p-values. So we're sort of working on thin ice in a sense, right? We're not 100% sure we are good to trust them, but we'll have a few contenders for our top model choices. And if we have a problem, we could go back and add that in. Alternatively, you could be checking residuals as you go, which is more work and it's slower, but it can also help you make sure that when you have your final model, that it is not going to, that you made decisions on those p-values and that you could trust those values. Okay. But once you have that, remember, we're going to replace any multicollinear predictors with alternatives to see if the model improves. And then we create the comparison table for our top 3 models, and we're going to choose our preferred models or final contenders using adjusted R-squared and the standard error. We're going to check the modeling assumptions to validate the preferred model or to help choose between final contenders. We can look at residual plots, and they should have no trends or look correlated. Should not have any changing variability. Should not be correlated in time if you have time series data. Should have an even spread above and below the mean. And if you've satisfied these things, you can declare your final model and then use it to make predictions. Okay. So that is going to be the end of 7.3.